We are to the point where we're ready to do the global pressure and winds diagram. And to do that, we have to talk about a few of the fundamentals. What you want to do is go back and make sure you've looked in your notes at the pressure and wind systems. If you haven't looked at that, this isn't going to make much sense. So first, go have a look at those notes, put this on pause, and then come back later after you have those in front of you or you've read them, and we'll go from there, okay? So the basic idea of the global wind system is that winds are created by pressure difference or gradients between different places. So where you have high pressure, the air would flow from the high pressure to some place where there's low pressure. So it goes from high to low. That makes some sense, okay? But what causes the pressure to be low or high? So there's two kinds of causes in reviewing those notes. One is thermal. So hot places make the air rise. That makes sense. Hot air balloons, okay? Hot places make air rise, generally speaking, and cold air places would have air sinking over them or subsiding, okay? And so what we get is a setting where we have high and low pressure associated with sinking air in the case of high pressure and low pressure with rising air. So this is what we call thermally induced pressure cells, which thermal in this case just means temperature. It can mean hot or cold. So in the simplest model, what we would have is it would be very cold up here in the north. And so we would write cold in the north and also in the southern hemisphere near the pole. And then it would be hot near the equator. And so we would anticipate the air rising over the equator and then coming and sinking over the poles, over this cold surface like that, and doing the same thing over here. Okay? And it would be the same on the other side of the diagram. I'm just going to do the on that one side. Now, what happens then at the surface, this was like a cross section, so the upper atmosphere, you can see the circulation going up, then coming back down. And then at the surface, we would have that cold sinking air would want to move to where the air is rising near the equator, so you'd have this happening, and you'd have this happening. Now that sounds all great, but it doesn't work that way because those arrows don't go straight. We have the Coriolis effect. So the Coriolis effect is that the Earth is rotating underneath the moving air or ocean current or anything else, a rocket ship, a jet, whatever. And so because the Earth is rotating, there would be a deflection so that the arrows would have to actually not go straight towards the equator, but they'd be deflected off to the right in the case of going from the North Pole to the equator, okay? So that arrow wouldn't go to the equator, it wouldn't make it, it would be deflected off to the right. And in the southern hemisphere, the deflection is to the left, so that cold air coming from the southern hemisphere, South Pole up to the equator, would be deflected off to its left, and it wouldn't make it either. So this whole diagram doesn't actually work. So we've got to start over, okay? So what I'm going to do is just go back and just get rid of all of these things here. And start over. So what we're going to do is we're going to say, okay, let's see how the Coriolis effect would actually work with all this. So we remember it's cold up there. I don't have to remind you that it's cold at the North and South Pole. That's pretty easy. So we'll leave the hot and the cold out of that. You know that the poles are cold and the equator is hot. So let's instead just get right to the work of figuring out what happens. So we have sinking air, and the sinking air wants to sink over the North Pole, but then it's going to go off to its right. So imagine you're the arrow itself, and you're moving off to the right as you move. It's to its right. It looks like to your left, right? But if you're the moving arrow, you're going off to your right, aren't you? Okay, and that's how to remember this. So the deflection of the Coriolis is to the right in the northern hemisphere, and it's to the left in the southern hemisphere. And so what we have is these high pressure cells where the air is sinking. That's something to keep in mind. The basic cross-section for high and low pressure is this. High pressure is where air sinks and moves out. So we have this kind of divergence or sinking air going out. And low pressure is just the opposite. It's where we have convergence and rising air. So that would be a low pressure. Anywhere in the world, those diagrams work cross-sectionally. Okay, so low pressure air is rising, converging. High pressure, it's sinking and diverging. Okay, because then of the Coriolis effect, I'm going down now to the South Pole. So look down there, I'm just writing a high in there. These are called polar highs. We'll label these later, but that's high pressure. It's air sinking. It's very, very cold. Of course, the air sinks over the cold surface. Just as at the equator, it's going to be rising. So what we do at the equator is we're going to draw, and these arrows show the air rising and then sinking, okay? Rising and sinking. And that sinking happens also then, if you look at that, sinking air, if you go back up to our diagrams in the upper right, high pressure is where air sinks, right? So we have sinking air, so we have a high pressure cell, and that basically just a little north of the Tropic of Cancer, and then looking down below the equator, I'm going to write in H down here. This is also high pressure, and later we will label those as subtropical highs, okay? So now we have high pressure cells, and since high wants to go out, the air sinks over high pressure, some of that air is going to sink, and it wants to flow toward the equator, but it doesn't go straight to the equator, does it? It has to go to its right. So that means we need to get rid of that and make it go to its right. So as it goes this way, it looks like that. So the wind created there, which we'll call trade winds, we'll label those later, functions like that. From the H now south of the equator, it wants to go to the equator there as well, but it has to go to its left, so it does something like this, okay? So those are called the trade winds, okay? So then the air, of course, is converging at the equator, so we can put a big L here to indicate that. It's also known as the intertropical convergence zone, okay? ITCZ, the intertropical convergence zone. And it makes sense because it's between the tropics and it's a convergence zone. So we have that sinking air over the subtropics that's rushing toward the equator, okay? So those are trade winds. All right. Now, we also have to think about something else. That air, let's look at that subtropical high in the northern hemisphere, okay? The air is not only sinking and wanting to go towards the equator, but it's also sinking and wanting to flow away from the equator the other direction. So what we have is air wanting to flow to the north. And what it does, though, instead of going straight to the north like that, it's subject to the Coriolis effect. So we need to draw it something like this. And in the southern hemisphere, it wants to go to which direction? The left or the right? Okay, to the left, correct? So we would have the airflow this way to its left as it flows, okay? Now, we're in an interesting situation here because we have these high pressure cells in the northern and southern hemisphere, these subtropical highs, and the wind flowing out of them wants to kind of head towards the poles, as you can see the one where we would be at. It wants to flow towards the pole, but it's not making it. It's going off to its right. But there is some net convergence between the polar high in the northern hemisphere where the North Pole is, and the winds coming out of that, and those winds coming out of that subtropical high. So what I'm going to do here, if you look up to the upper right again, you've got two pressure cells. You've got highs and the low types. What is going to be found in this area right here? Is that going to be a high or low pressure cell there up in the kind of subpolar zone of the northern hemisphere? Okay, it's converging air. So if you look up to the upper right there, you see that low written in there. That's convergence. So that's what we've got going on there. So I'm going to go ahead and get rid of the question mark, and we're going to put a low in there. That's a zone of convergence. So very consistent with what we see up the upper right there, okay? And as well then, in the southern hemisphere, we have the same thing going on. We have winds converging between those subtropical highs and the polar highs. So down here, this area here, what do we do? Okay, what do we put there? So again, it's going to be the same thing. It's converging air. Looking at the upper right, you can see the low pressure is converging rising air. And so those are also going to be lows down in that area. And so I'm going to just write a low here, okay? So what we have now are wind systems and pressure systems. Starting all the way at the top, we've got polar highs with polar easterlies. We've got what's called a subpolar low. We'll mark those up in a minute. Subtropical high with its westerly winds and so on, all the way down to the equator, and we have a low there. So basically it goes high, low, high, low, high, low, high if you start at the very top in the northern hemisphere and go down. So there's a sequence of high, low, high, low, high, low, high. Okay. Now, what we said was that the polar highs were thermally generated. It's really, really cold there. The equatorial low is thermally generated as well for being very, very hot, okay? But in between those zones, we have something different going. So let's go ahead and write in the names of all these. So this is a polar high. And down the southern hemisphere, it's also a polar high. We have this zone of subpolar low, where that L is. I'm going to write out here in the outer margin. And then we have the subtropical high in that subtropical region, kind of right on the edge of the tropics. Subtropical high. And then the equatorial low, we've already, we can write that in again, or the intertropical convergence zone. And then the high pressure in the southern hemisphere bears the same name as the one equidistant in the northern hemisphere. It's called as subtropical high. Hope you can read my writing here. I'm just learning how to use this program. You might have seen my first try at it in the first unit. So the subtropical high in the southern hemisphere there, and then in our simplified model, there's a subpolar low as well down here, just like there was in the northern hemisphere. So it's a symmetric model. Subpolar low, okay? So those are the pressure cells, okay? So all of those lows and highs, those are pressure cells, and between them happen the winds that they create because of their pressure gradients, some stuff that you've already looked at. Again, if you haven't looked at that stuff, you might want to go look at that before you really try to get a handle on what I'm doing here, okay? It'll be much easier for you if you do. Now it's time to label those winds, okay? And I'm going to write in, let's see here, up here, polar easterlies. Okay, and in the southern hemisphere, same label, same kind of winds. And by the way, we name winds for the direction that they come from. So the polar easterlies come from the east, and it kind of looks like northeast there in the southern northern hemisphere, and from the southeast in the southern hemisphere. Look up to upper left of the diagram. I'm going to write in, because I know some of you probably aren't real comfortable with me saying northeast, south, and west, okay? So this is a basic layout of all of that. Okay. And so these are the kind of cardinal compass directions. And when we name winds for the direction that they come from. So if the polar easterly, it should come from roughly the east, with some variability, but that's a basic idea. Okay. So this wind down here now, basically in our latitudes where Oregon, we'd be right in the middle, right? So this would be Oregon, and we are dominated by what we call the westerlies. Okay, and they're basically from the west. They kind of look southwest there. That's fine, and they actually vary depending on where the weather systems are. And so typically those are strongest for us like in the wintertime. But they're a general circulation pattern of the middle and upper middle latitudes. All right, now going down to the southern hemisphere, let's also label the westerlies down there. Where would those be? Looking at the southern hemisphere, where would the westerlies be? So they're symmetric to what they were up above. And so is it right here? The answer is yes. So it's right here. We'll call these the westerlies too. And they're kind of northwesterly, but we'll just call them westerlies. That's a convention. And what we end up with then is one more set of winds to label. And where are those? So those are in the tropics. And those, I mentioned before, are called the northeast trade winds. Why are they called trade winds? Because world trade, when Europe was the kind of colonial power beginning the 1500s, world trade focused, among other places, between the so-called New World and the Old World. And the way you got from Europe to the Americas was you took the trade winds over. And then you come back on the westerlies as on a sailing ship back towards Europe. Okay, so in this general model, then we've got northeast trade winds. Where are the other trade winds at? So yeah, down there. So let's write in southeast trade winds. Okay, southeast trade winds. So now we've got all the winds and we've got all the pressure cells. Wow, that's pretty good. That's the basic diagram. Now, in a class where you memorize and take tests based on memory, I have my students draw that. You know what? You guys lucked out because I'm not going to ask you to do that. You got the notes in front of you. How hard could it possibly be to do, right? But what I am going to do is ask you about your understanding of all of this. And so in the notes on winds, the same unit where we started with this, there is a description of what causes these pressure cells to form and then the winds that are driven by them. Okay, so there's a whole bunch of detail there. So you should study that enough to at least understand a little bit of the detail. But again, keys here are what drives this. It's thermal generation of lows and high pressure. The equatorial low, hot rising air, sinks. It rises over the equator, sinks over the subtropics. And so if you look at this, then we've got the thermally generated low pressure cell at the equator, and then the polar high is also thermally or temperature driven. But then in between, where you have the subtropical highs and subpolar lows in both hemispheres, those are what we call dynamically driven. And they're basically collisions of air, or air that's driven not directly by thermal, but just a second order thermal. So for example, the sinking air over the subtropics, it's not sinking there because it's cold over the subtropics like it is the poles. That's not a thermal thing. It's just that the air rose at the equator, which was thermally driven, and then what goes up must come down kind of thing. It's sort of like taking a garden hose, spraying it way up in the air, and then watching the air or the water sink back down kind of a little bit off to either side, like fountains do, for example. That's the dynamically driven subtropical highs. So that's the basic diagram. What's kind of amazing about this diagram is that it's driven by movements of the subsolar point. So one thing to kind of think about is that, in the days, I'm going to draw a couple things in and then erase them, but I'm going to draw the Tropic of Capricorn in there a little bit there, just little dots there, right? And then the Tropic of Cancer up above there, just parts of it. Remember that the subsolar point goes between those two places over the period of a year. I didn't get the right places, didn't quite, did I? So these are the areas that get the most sun. And so the subtropics and the tropics are the warmest parts and where we have the trade winds and again, the movement at subsolar point. So what happens in that is that we have, like, for example, in December, the subsolar point is down that southern hemisphere, and in June, it's up here. And guess what? As that subsolar point moves back and forth over a period of year, anywhere in the tropics has exactly 2 times when the sun is directly overhead, as we learned. And here's the thing. All of these winds and pressure systems are pulled a little bit north and south by the season. So that intertropical convergence zone that we see here, and I'm just going to circle it, that zone actually moves to the north and south. So what would it be doing right now? Well, as I give this, it's in April. So as a subsolar point is moving north, it'll be up to our Tropic of Capricorn in not too long. So is the intertropical convergence zone moving north and everything that flows with it, okay? And so then it will move to the south. After June 22nd, it'll start moving south, and it'll come over the equator in September again, okay, September 22nd. So we have those movements back and forth, and that pulls these winds and pressure cells with them. I'm going to go ahead and leave that in there. I think that the December and June, those are good ideas just to kind of remember, right? And that subsolar point moving back and forth there. I'm going to write that in there too. So subsolar point. Okay, it moves back and forth. All right. So that's, in a way, it changes the seasonality. So any of the weather, for example, created by the intertropical convergence zone at the equator actually moves north and south, depending on the season. So we'll get to that later on. So that's the basic model, and I will refer to this quite a bit, so you'll want to keep that in mind. Hope this helps.